And after compression, guess how small it becomes?
48.
The most, it became 20 using the richest compression. I don't know how much it would have been if they have 3 compression things. So they said internet quality, which is sort of the best they have. So that's pretty good. Okay. So what I'm going to do is take 4 case studies of IPC. Okay? And non-blocking I/O will come at the end. Okay, just because it's the most complex. And I'm going to gradually migrate to it. I'm going to start off by something that is not even distributed. It's a system XINU that I talked about. XINU stands for, anybody want to guess what XINU stands for?
XINU is not UNIX.
Very good. It's a recursive. It's both ways. Okay? And so we're going to look at both the design and implementation of it, just to get an idea of what, how these things are really implemented in the operating system. Okay? And then we'll go from there to UNIX pipes, which are also an IPC mechanism, to sockets, and then NIO. Okay? So XINU is not, XINU is an OS, and it provides IPC facilities between what it calls processes, what are actually threads. Okay? Everything runs in one address space. Okay? And at one time, that some PC platforms were also that way. And it's amazing, this computer on this computer is so much faster than the first workstation I used. But it's no faster. I mean, the CPU is much faster, but the software is no faster. And part of the reason is that those things were these Xerox computers that I had, and they were all in one big virtual address space. That's only because we have gone into the software engineering thing, which principles, separation, different address spaces, that things get slower. Okay? So this was meant for simplicity of design use. So the communication is between threads in a single process. Well, it's not a single process. Everything is a thread. So in a single computer, all sharing one address space. Yeah? Donna Boggs' reception is going on right now. Okay? Multiple address spaces not supported in XINU, which is also true in several PC OSs. Okay? And the operations we had there were send, okay, process ID or thread ID, and some int value, 1 word value. Okay, life is easy. 1 byte message, one word message. Okay? And you didn't block. Okay, what does that mean, you didn't block?
You send it and then assume that when you send it, you takes care of it.
Yeah. So you keep going. You don't wait. You don't, so if you're in a distributed world, you have to know whether the message got through also or not. But we are not in a distributed world. So it will get through. If it won't get through, that means that the OS crashed, that means you've crashed, that means you haven't harmed, So you have a bigger problem. Okay? Receive. Okay, you send an int value, you receive an int value, it's just a function. And should this be blocking or not blocking, and what would it mean?
Well, that's in.
Okay, so what would blocking mean?
You hold that.
You wait until you get the end of this.
You get an int. And non-blocking would mean who knows what.
Say maybe I'm open to receiving one, and then you processing, and then maybe trigger an interrupt when you get one.
That's what NIO does. See, you just design NIO. It's not so hard. Okay? But we didn't do that here. Okay? You would just go and say, if there's a message, I'll take it. Otherwise, tough. Okay? And did somebody else have something?
Oh, yeah, I was just going to say, implicitly you have like callback or something to handle it.
Yeah. Or you either have a callback, okay, which is the high level thing, or you go and make a call like a select call, where you say, I have gone and registered my interest in all of these operations. Now I'm going to block, waiting for the next operation that occurs. So no callback, you make a blocking call. And in the blocking call, you get back and saying, by the way, that receive succeeded, or that send succeeded, which is exactly what the NIO is giving you. Okay? And receive clear, which just says, it's really polling. Do I have a message now? Do I have a message now? If so, I'll take it. Okay? So if you are going to be receiving from multiple parties, you can't be blocked on one particular receive. So you go and just try on all the ports and say, okay, otherwise I'm just going to do something else, wait. get a semaphore. So this is non-blocking. Okay, semantics easy. Okay. IPC, that's a full IPC mechanism in XINU. Okay. So how would you implement this? How would you implement send? Now, those of you who have taken OS, put on your OS hat right now.
I would imagine you'd need some form of mailbox where these messages get collected. So.
Okay, so you would have to put some mailbox. You meaning, how many mailboxes would there be?
Maybe one per thread, so maybe a certain memory offset from the beginning of that thread's memory block gets designated as its message receiving inbox, and then send puts your expression in that thread ID's mailbox.
So you're saying, you know, my address space, the thread has some address space, and somewhere in its address space you will write this word. That's kind of tricky, right? Where in its address space would you write? Because it might use that address space.
Well, you'd have to designate, there'd have to be some sort of, but then I guess you get into virtual memory, which you're not supposed to use,
So you're saying basically the OS and the are sharing this memory, and we're writing this there, and somehow we have to make sure that the compiler doesn't generate instructions to go and put things in there.
Well, maybe you could put maybe sort of a central mailbox system. So the OS has a reserved system of mailboxes, and then it populates it for each thread.
Okay, good. So when the OS reserves space for a thread, that space is called what? There's a technical.
The OS reserve space?
Yeah, for a thread. For each thread, there is some data that the OS keeps.
Well,
That's what you're saying, right?
Yes. Well, for the process control block.
Okay, so context block, process control
Yeah,
block. Okay. So there is this thing. So you have a process table basically, and for each process ID is just an index to a table. And that table has entry about your, what all does the context block have?
Current registers for the process.
Okay.
The next instruction in the process.
Okay, that's register. And whether you're ready or not ready,
State.
your state. Okay. So we will go and put into that box also one message word. Okay. We could be more fancy, but since we have limited things to only one word, what's one word? Okay.
What about getting concurrent messages? Yeah. Don't you need a queue?
So that's a good question. What if I send a message to process and I send another message before the receiver gets it? What should be the semantics, and what do you think is the semantics? Focuses on simplicity and implementation. Sorry?
Dumb override.
The last one wins.
Either you override or you say mailbox full. Sorry, ignored your send. You get an error back. Right? That's a little better, isn't it? Because the next sender gets to know that he sent. If you override, then the sender that had sent the data doesn't know. So it's better to go and tell the new guy that, hey, try again later.
Yeah.
Okay? So that's my send.
So send can come back with like a -1 or some error value or somewhere in there.
Didn't succeed. What will receive do?
Just check your mailbox.
Okay? If the mailbox has something, so I have to not only record my message, but I also have to record the fact that there is a message.
Right.
Okay? And then the receive will say, do I have a message? If so, grab it. That's what receive clear will also do. And if not, what? Block. And you're the OS, you can block. Okay? And your threads or processor states are running. What else? Ready, but not running. Very good. Or waiting of some kind. Maybe I'm sleeping, maybe I'm waiting on a semaphore, and we'll just say you're in the receive state. Okay? And then, so what does send have to do now? It has to put the data in the buffer and do what else? Do what else?
Signal the other thread to let it know that, hey,
If there is somebody waiting, go and unblock it.
So notify.
Okay? That's it. So you have a data structure with each thread, your stack, registers, program counter, your priority, okay? Your status, are you ready, current? And we'll just go and add the received word and whether you have a message or not. And my send goes and says, if this word, there's no word received, then do this, otherwise we'll go and just return some value. And otherwise you assign the value received word, you say has message, And if somebody is waiting, if that process is waiting, then you ready it. Okay? And ready is magic, some magic thing that you do a lot in OSs. We'll just go and reschedule it. Okay?
Would it be a design decision to say, instead of having a separate Boolean value for has message, just have a special code in the mailbox that says, there's nothing here?
But what if you want to send that word?
Well, that's what I'm saying. Besides, it reduces your possible message space by 1.
Yeah. I mean, that's a classic example. That there's no null pointer. In objects you have null value, null pointer is absence of value. In simple values, there's no absence of that. I told you I learned a lot from Doug Comer, who invented XINU, and he had these 3 principles he would always emphasize: memory is cheap, caching is wonderful, and late binding is wonderful. Okay? I forget what the third one is. I think I might have invented that because I believe in that, but I forget what his third principle was. So memory is cheap, even though he made an operating system that had a very small footprint. Okay? So you go and say send to 5, you get the 5 value, and this is true. You say 6, just goes in, doesn't do anything. Receive operation, if there is a word received, if there is nothing received, then you put yourself in the receive state and you block. You're the current process, right? You're the one executing. So you want to go and put yourself not current, and you want to reschedule so that somebody else can execute. Okay? And at the end of this, when you get unblocked, you will start execution here. Okay? At this point, you say has messages fall and return the received word. Okay? So if you did block, you would resume at this point and you get the message. If you didn't block, you would just go here.
And this is assuming that second part doesn't get interrupted in between
Yeah.
calls.
Right. So this is being done in a system call.
Okay, so
System call means that you block. By the way, how do you make sure that you don't get interrupted? Now, if you're above the kernel, you use semaphores, right?
Right.
But semaphore has to be implemented also somehow. So how do you make sure that you don't get interrupted?
Disable interrupts.
You disable interrupts and enable interrupts. Okay. So here we go into receive state, we get the value and return. Okay, we get into the ready state, we get the value 5, we're going. And receive clear, simple. A word received, return no val, and otherwise you just return. Okay, maybe this can just go here. Oh, I should really call it receive clear. I guess I wrote this code in a hurry. You all use Unix pipes in a command line? And that's
magical data channels.
Redirect the output into the
okay. And so that's IPC. When I say ls pipe to more, ls is sending messages to more. Or what you guys use more? I guess today you don't use more because you're a score bar. Okay. So a pipe is both a user command and an API call. Underneath, the user command is implemented using call. So this pipe call is returning what? How are pipes implemented?
Somewhere in there, there's file descriptors.
Okay, so one of the goals of pipes is to blur the distinction from a design point of view between. So a design principle is that this IPC should look like
Reading from a file.
writing from a file.
Yeah, I guess with Unix, it's like everything is a file, and the files are all, bit or byte oriented. And so when you do a pipe, it's taking the standard output from one thing, just the bytes, and feeding it into the standard input of another. And another way you can do that is just have the command read a file. So it's it blurs over actually writing a file and reading it right back.
Or basically, it blurs between I/O. It regards IPC as I/O, and there are limits when you do that. But that was the principle there. And the nice thing is that when you make things uniform, it's good. You have to learn a fewer things as a programmer. But the main thing is this late binding. That means I can get the input from the user console, or from a file. That's because of my file I/O, or I can get it from another process. Oh, what a wonderful idea! So this was really a brainwave, that's the basic principle. And how is this? So this is I/O redirection. Okay, that I/O can be redirected through a file or to console. And how does I/O redirection really work? Do you guys know? I mean, it happens, right? When you use the shell, it happens. What is the shell doing to do it? What if you had to write your own shell? Which when I taught Oasis, people did.
We do too. And whenever we show, I just consume this API.
Sorry?
Right. We just use this API.
What does it do? And it's okay. So what is the API?
You specify inputs. There's two types of pipes.
Yeah.
In and out.
Okay. So
essentially, if you want bidirectional communications, you really need two pipes. Essentially, pipes are unidirectional.
Right. So you get a reading and writing. So you get a writing descriptor, you get a reading descriptor. Pipes are, by the way, one. Pipe can be it's actually very complex. You can have multiple processes reading and writing. Okay. So that's what we want. We want our process's standard output to become the output descriptor in one case, and the standard input to be the input descriptor in the other case. Okay. So we have two different processes, ls and less. Okay. And how do they? I mean, they're two different processes. How do they? Which one makes the call?
They both make the call. So from the point of view.
Okay, so ls makes the call. How do they form one pipe then? Pipe has to be made. The call has to be made by one process. It can't be made by two processes.
Well, the one generating the output would have to go first, and then
okay, then it goes
one
in.
accepting the input would pop.
How does it even know? How does it even know about the other guy?
It self-function. So it takes wherever the first program would write out to, which is standard output. It basically the first program just assumes it's still writing the standard output, and then Byte just takes the bytes from that standard output and maps it to what the second program thinks is standard input.
I know. That's fine. That's exactly what was.
But how?
But how do we know that process A and process B are connected in a pipe, and process C and D are in another pipe? How do we, if each one is working autonomously, how does the pairing happen?
The shell.
Shell?
It has to be the shell because each individual thing doesn't know about whether it's in a pipe or out of a pipe or what the next thing in the pipe is.
So the shell has to make that call.
Right.
And somehow then pass the descriptors to the two processes.
Right. And we're not just talking about the context of using it as a command reaction programs.
Yeah. The shell is making the pipe call.
Right.
What does the shell do then after it goes in? When you just say ls, forget pipe. What does the shell do to interpret ls? Oh, not ls is not a good one. Let's go and say Java C. Okay, ls is a little different. Actually, ls, that's a system built in from CD. But let's just say it's running Java C. What does it do?
It's going to fork and execute.
When you fork, what happens to the child process?
It basically, it's memory stage. Just wipe out, replace it, whatever.
That's exactly.
Oh, sorry, yeah.
Fork, what happens?
You just copy everything, and then
You copy it, including your context block. That context block has file descriptors now. So both children basically have context blocks that are copies of the parent process. And that's how you have this shared memory. Because you need some shared memory right now so that the two descriptors tend to be two ends of the same pipe. Okay? So I think we'll go through this in slow motion here. So focus on late binding of teletype I/O source and sink, string-based communication. And this is all intra-computer message passing. Okay? You can't have the shell, these two guys are being bound by one process, which means they both have a common parent process, which means they can't be on different computers. Okay? So with XINU IPC, we were bound to the same threads in one process. Now we are different processes in the same computer. Okay? We are going to gradually migrate to sockets later. So forget these terms, bound port and all. When I taught it last time, I I came up with a big theory before I talked about these things. So we couldn't get to do anything because I was talking about this big theory. So when I do something like this, the command interpreter connects output of process to input of another process. And how do they go in? We basically have this situation. You can have multiple people writing to a port and multiple children reading from the port. Why? Because the command interpreter can fork 5 children, all of which inherit the same type descriptor. So when a descriptor is open in multiple processes, every one of them can write to that file at the same time, the open file. Okay, they're sharing one read-write mark. So if I write and then you write, you write at the next file after I write. Okay? But typically pipes are not used for that. Pipe typically is between 2 processes. And child inherits file descriptors and environment variables from parent process. Okay? Environment variables are like what you were talking about. That's certain area in your address space to which the OS writes. Okay? And so that is what was allocated, and that's in user space, whereas the context block is something that's in the OS. Okay? And it's a much more scarce resource. And here we have, typically 0 is the standard in, 1 standard out, 2 standard error, and you can have in here, and this is your environment, class path, so forth, that's in your address space. Okay, and when you do child create this, you get a copy of both the environment and the file table. That's the principle being used here. And so parent process does a pipe call. Now the parent process has pipe in and pipe out, 2 new descriptors. Okay. What it does next is forks a child. The child will go and get all of these descriptors. One of the child is going to write and one of the child is going to read. So each child closes one of the descriptors it gets. Okay, it knows. That child is still a shell, by the way. Huh? That child is still executing the shell program. So this is all happening there. It's not in the exec so far. Okay, and so one guy's got the pipe out, and so we've got these, and now I'm just going forward quickly. We've ended up with one guy with the pipe out, one guy with the pipe in, and now they're connected to each other. Okay, and I'll just stop at this point. And this is where I want to point out that all this code of redirection, closing descriptors is happening in the shell. And when you do the exec, LS doesn't even know what happened. It just goes and says, oh, whatever my standard output is, I'm going to write to it, which happens to be pipe out. So your code, the program you wrote, is oblivious to IO redirection, and that is why they've separated fork and exec. You always wonder, why are fork and execs not combined into one call? Because they wanted pipes. They wanted IO redirection. And we allow the fork to do the IO redirection in a shell, and the exec to actually do the program. Okay? Okay.